Okay, hi. I'm going to talk about zero knowledge work, what to trust the cloud or crowd with and what not or how. And I call the talk Lessons from Vanity. We'll see why. Uh, I work for High Solutions in Berlin, security consultancy, specializing in technical topics like pen testing, forensics. We're also hiring, so if you want to move to Berlin, pass me a note. I live in Warsaw, and I'm interested in the edge cases of information security, like ICS, where it gets very physical, cloud, where it gets very virtual, or crypto. This is where I come from. Today it's not about ICS, but about the other two, cloud and crypto. Okay, as we all know, as you know, more and more processes are transferred into the cloud or thrown at crowdsourcing. I don't have to name all the examples, you know them. Why is this happening? You can make a big analysis. The short one is things are being networked more and more, so it's possible. There's some efficiency gains, division of labor, capital intensity. This is not specific to cloud. This is happening in other parts of economy as well. And then it's also a kind of fashion or buzz, so everybody thinks they have to do it, they have to sell it, they have to be part of it. Cloud and crowd, I said. What is cloud? You can make complicated definitions at different aspects and so on. For us today, it's just somebody else's computers, and crowd is other people's computers. It's not the same. In cloud, you think more about someone who owns a lot of computers, and in crowd, you think of a lot of people who own one computer or a few computers each. But in the end, from the confidentiality perspective, it has a lot of things in common. You give away things that should be private, that you want to be private, to someone you don't know perfectly, you cannot control, and so on. And so are outsourced to the cloud or crowd security relevant processes. For example, bug bounties is where you tap into the power of the crowd to help you find bugs. And also security relevant calculations. For example, hash cracking. You can buy that as a service in the cloud. This is only the beginning. More will come. And my first question is this a good idea to outsource security relevant calculations to the cloud? Do you think? Good idea? No good idea? Depends on the criteria, of course. So I made a simple chart. It's too simple, so it's not true. But there are things that you could call a good idea, like bug bounties. They have a lot of advantages for the ones running them, and sometimes also for the people participating. There are some things that are definitely bad ideas, like there are services where you can order handmade passwords that were handcrafted specifically for you. I didn't bring the screenshots, but you really can buy these things. Or explicit password checks, like sending your password somewhere and ask the service, is this a good password? Because what do you do when they say yes? You don't know where it went and what else is gonna been done with it. Then there's a lot of things where it really depends whether it's a good idea or not. Storage is such a thing. Depends a lot on your requirements. If availability is key and confidentiality doesn't really matter, then the more storage you get and the more distributed, the better. So then cloud is certainly a good idea for you. Hash cracking depends on how much you trust the service, where you got the hashes from, what you will do after they have been cracked or they couldn't be cracked, and so on. And also with entropy, you can gather entropy from a lot of sources. This can be a good thing, but you have to be careful. How about creation of asymmetric key pairs? So asymmetric cryptography, you usually have a key pair, a private key and a public key. and they have to be linked mathematically, so they usually are created together in some way. Should you outsource this to the cloud or crowd? No. The name private key says it, basically. It should be private. This is why it's called private. And that's maybe the worst idea of what you could outsource to. One of the worst ideas, what you could outsource. It's easy to come up with a bunch of examples where it's safe to outsource something, but they're not very interesting. Like, you can just ask for a password at some service and then not use it, or use it for something that's irrelevant. Okay, trivial. You can request some randomness and incorporate in your state that is already a good random state, and not break that state. That can be okay. You might even, now it's getting more complicated, make a password, hash it with a cryptographically secure hash function, so one that can certainly not be reversed and maybe even takes some time to calculate, so to make brute forcing harder. Send it to a database and ask, has somebody already used this password or this hash before? But you should only do this if you're really sure that your password is not brute forceable, so not in any word list, not too short, not and so on and so on. And if the hash itself will not do any harm, because sometimes it's enough for people to have your hash for some attacks. So you might take another hash function that is used nowhere else, and so on and so on. So there's a lot of ifs here. So it quickly gets complicated. A more interesting example that I stumbled across a couple of months ago is the creation of Vanity Bitcoin addresses. So there's 3 terms in here. What is Bitcoin? Was it a Bitcoin address? And what is a vanity address? Bitcoin. Okay, you can say, that's so 2008 or 2013 or whatever, depending on when people came to the topic of Bitcoin. And it's true, and this is not a talk about Bitcoin. I'm going to take in something from Bitcoin to show another point. But for that to understand, I need to show you a few things about Bitcoin that you might know or not know. Here, for example, is the development of the exchange rate. Oh wait, that's the log scale. This is the better one. That's the real scale. Yeah, it has a long development. A lot of money was made and lost with Bitcoin. It's still alive. People say it's dead. It hasn't made its way into general life. So it's used worldwide, but not a lot. So transaction numbers are still ridiculously low compared to other payment systems. But it has, it was the first with a lot of interesting ideas, and it's still the most used and so for some reasons the most interesting cryptocurrency. Not technically, mathematically maybe, but for the whole ecosystem and so on. So what's Bitcoin? In October 2008, somebody called Satoshi Nakamoto wrote an email to the cryptography mailing list that he came up with something new, with a paper. Here's the paper, first page. It's just 9 pages, so if you're interested, really read it. Read the original papers. It's worth it. And the main properties of this Bitcoin that he invented are listed here, and we don't really need most of them today, so I'll be just very short. So digital currencies are easy in a way. You can build some parts of trust with digital signatures, but information has one disadvantage, or one differentiation from physical currencies like gold. You can copy information almost for free. So when you spend a coin, somehow it has to be prevented that you spend it another time, because you can just keep a copy. and nobody would trust the coin if they wouldn't know if they had been spent or not. So you need something to keep track of what was spent or not. He proposed a peer-to-peer network. So you don't need any central authority, no central trusted party or mint. Anonymity is possible. And you need a way to introduce new coins, and he used the hash cache algorithm for that. That was invented in 2000 or 2001 as a proof of work. So this is one of the most interesting ideas. To create coins, you need to work, to calculate a lot, and everybody will believe that you did this calculation or did the amount of work, statistically at least, so that you earned this coin. And the most genius idea, and it was to use this coin generation process at the same time to solve the double spending problem. But about this on another day. This hash cache, what is it? It's a easy and nice thing. You take some random thing, a string or number, hash it. You have to agree on the hash function before, and just check if it starts with a specified substring. For example, with zeros, with a certain number of zeros. Sometimes this will happen by chance, and usually not. And the probability that it will happen depends, of course, on the length of the substring that you demand. And if there's a good hash function, there is no shortcut. You cannot calculate a string that would hash to something like 000 in an efficient way, other than brute force, because if so, the hash function would be broken, would be not pre-image resistant. So this is exponentially expensive in the length of the substring. So not only more expensive, but to the power of the length. So means significant lengths are intractable. You can only do it for a very short length. And this can be used as a proof of work because it's a lot of work to calculate it, and because it's scalable. So you can set a certain difficulty and make people work for it, and you can check whether they achieved it or not. Okay. You can use this hash cache or similar schemes for different things. The original idea was to use it for spam protection. So before you are allowed to send out an email on an SMTP server, you have to prove you did a little bit of work. This will make it very expensive to send very large amounts of emails. It wasn't really implemented in practice for several reasons. You could use it for cloud performance assurance. That's another subject of research that some people are doing. So you can try to track if your cloud provider, where you are renting a certain service, like number crunching, is really doing a lot of work for you, like you're paying. This is also not what it's about today, because we're not about performance, we're about confidentiality. And of course you can use it for the mining, so for the creation of new coins. And mining is basically this thing. Anybody can look for some randomness. You don't start with 0, but you have to include the last block, and this will become the blockchain. So that people know where you're at, what you're signing, and then when you find the bit of randomness that brings everything to the 000 difficulty length, then you're the one who mined the coin. Like mining, you found the bit of gold, and then it's worth something that is defined in the standard, like 50 bitcoins, 25 bitcoins. So quite a lot of money, but doesn't happen so often. Okay, we haven't said yet what a coin is. A coin is simply, no, it's not that simple, is a chain of digital signatures. So we saw how coins are created, and then a coin can be transferred from one owner to the next. Better to say from one address to the next. And the owner, an owner means the one who knows the private key. Because he can sign for digital signatures, you need to know the private key. He can sign the hash of the previous transaction and the public key of the next owner, so the one it's supposed to be sent to. And this will be appended to the coin, and then the coin basically tells everybody I went there, and everybody can check the whole chain because the public keys are public and they are known in the peer-to-peer network. So the coin. We said signature. What kind of signature is this? Digital signature, of course. And in Bitcoin, it's the ECDSA algorithm, the elliptical curve digital signature algorithm. There are certain reasons why they choose this signature scheme. One is that elliptic curves make keys shorter. So for the same security level, you need shorter keys, and that means shorter addresses and so on. And they picked a special curve because to do elliptical curve calculations, you need to agree on a curve, so a mathematical structure that you do calculations like additions and multiplications in that work a little bit differently from standard numbers that we usually use. This is what makes them more complicated and what makes them harder to break and a way to reverse certain operations in them. And they picked one that was not in the list of usually recommended elliptic curves, like from the American Standards Institute NIST, but one that was in a deterministically constructed. So when somebody gives you a curve, they might have built a backdoor in it. So they know tricks how to move around it, how to calculate faster within it, and you don't want that. And this curve here has the nice property that everybody can see how it is developed, and it's an easy process. There's basically not much room left to hide a backdoor, and it's also quite efficient to calculate on certain processor architectures and so on. So a private key in Bitcoin is 256 bits. And the public key you just calculate. So you pick a private key, for example, by random, and then you just calculate the public key by multiplying the private key with something called the generator of the elliptic curve. Generator is basically one element that allows you to move around all the points of the elliptic curve. And it's always, because it's discrete, always modulus some parameter. It's not really important here to understand what we're going to. Okay, now what is a Bitcoin address? We're almost there. A Bitcoin address is basically a public key. There's some steps in between. It is hashed and hashed again, and it gets a prefix to convey some more information, and then it's encoded in base 58. We'll get to that. So this is one example. This is my address. My just means that I have the private key for this on my laptop, so I might transfer the money that gets there somewhere if I don't lose the private key. Anybody else who steals the private key or can guess it can also owns the money in that way. So what is this base 58? It's those characters. Do you see what they are? Isn't that base 64? What's the difference? Anything missing? Anything too much in there? Something should be missing? Missing? What's missing? So the two special characters of base 64 are slash and dot or plus are missing, but then we would be at base 62. What else is missing? Why is that? Okay. So it's this base 64. You take away the special characters, plus and slash, and also the ambiguously looking characters, 0, big O, L, and what's the other? I. Capital I and L. Yeah. So you get to 2 times 26, that's the alphabet, plus 10 digit, plus 2, that's the special size, that would be base 64, minus those 6, so 58. How much information can you put in there? Almost, 5.9 bits per character. So that's only a little less efficient than base 64. If you get to long numbers for bit fields, something like that, it's not so good because it doesn't align with bytes. Okay, it's not only used in Bitcoin, also in other places, sometimes in little variations. So, and the third, we had Bitcoin address, and we had Vanity Bitcoin address. I just copied the definition from Wikipedia. What is vanity? The excessive belief in one's own abilities or attractiveness to others. And then it goes on that it used not to be so negative like it sounds today, and just meant futility. So in vain, you still have it in vain. I did it in vain. It didn't have any fruit. And there was vain glory, an old term, because vain was not negative, but the glory had the boosting part in it. Okay, you can make some puns out of that. I'm skipping those. And there's the 7 deadly sins: lust, gluttony, greed, sloth, wrath, envy, pride, and we're already at 7, so there was no space left for vanity. But luckily, Pope Gregory said that vainglory is a part of pride. So we're talking about a partly deadly sin, part of a deadly sin. Now, seriously, a vanity address is just nice looking, not really rememberable because they will still be a little bit too long and complicated. We'll see why, but still nice looking address with a hint at something like the owner or the organization. This defeats one of the aims of Bitcoin because we wanted anonymity or at least pseudonymity. And if I call my address, I don't know, One High Solutions something, then a part of the anonymity is gone, of course, so you have to think about that. But you can have example like one pay me, and then it goes on. With some human-readable substring after the leading one, you always have a leading, usually one, can be something else. And the beginning can be nice looking. That's a vanity address. And why should you outsource this? Why would you get the idea? Because pretty addresses like this, they need to be calculated. This is this trial and error thing we talked about that's exponentially expensive, like mining. So it makes sense to give this task to those who have the right hardware in place to do it efficiently. And nowadays, or for mining nowadays, you need special hardware, ASICs, and big installations of them. And here it depends on the length of the vanity address, if you can do it with a standard computer or not. Okay, there's tools for it. VanityGen, for example. open source. Here's an example. To generate something that starts with one boat, it took around 10 seconds on a standard PC. There's also versions doing the calculations on the GPU. Obviously, good idea. Still much less efficient than ASICs, but better than CPU. And there's Vanity miners that automate the process of outsourcing this to the crowd. Now we're getting somewhere. So my private key in the cloud, hadn't we said that was a bad idea? Because bitcoins have been stolen really for a lot of reasons. Of course, stolen keys, stolen wallets, like that's the standard thing. But also from things like brain wallets or poorly sourced randomness. What is a brain wallet? A brain wallet is the attempt to store bitcoins. What you need to store is basically the private key to a coin in memory, human memory. That therefore a brain wallet. Because as long as the key is not recorded somewhere else, the coin exists only in the holder's mind, meaning that unless Bitcoin is seriously broken, there's no way to transfer the money away from your coin, from your address. It has some drawbacks if the brain wallet is forgotten or the person dies, or the coin is lost forever. So the money, the coin will have the amount that it got forever, unless Bitcoin is broken or somebody changes or the community changes the protocol. Early brain wallets just took a passphrase and hashed it, and there they had the private key or a sequence of private key. If you want to make a whole wallet, you need more than one key because you shouldn't reuse addresses. So basically, you need one address for every transaction. And this was not a good idea because, as we find again and again, humans are no good source of entropy, and this really hurts in this case. And as we speak, if you make a brain wallet out of a passphrase that is in some dictionary that is too short, too easy, your money will be taken away in minutes. It will be gone because some people, it's not a lot of them, maybe a dozen people worldwide, they specialized in just draining stupid brain wallets. And somebody wrote about those, for God's sake, don't do it. You may think you are smart enough. So did everyone else who got robbed. Humans are not a good source of entropy. You have a scheme, the space of all schemes you're likely to have probably only has a few bits of entropy. A random phrase in a book, there are only about 30 bits of sentence selection in a library. Oh no, you're not listening to me, are you? Oh crap. You think that 8 characters and 1 from each character class applies here? Website security might have to deal with 1,000 attempts per second, but some dude with a FPGA farm is probably pre-computing 1 billion brain wallets per second. Just stop. No. Okay, so really don't do it. Brain wallets, it still can be done if you take the entropy from somewhere else. So some clients allow you to translate a good random address into a series of random words that you might be able to memorize, but that's something 13 words upwards or 20 words. So a lot to remember. And the other example was poor randomness. It happened, for example, in 2014. The service blockchain info, one of the big services in the whole ecosystem, they run the tool where one of the tools where you can look at the whole history of the blockchain. It's public, so everybody can look at it. Everybody can have it on their clients, but they make it easier to look at what happened in Bitcoin. And they also offer online wallets. It's another question if you want to use online wallets, because one of the ideas of Bitcoin was decentralization, and if you outsource the operation of the wallet to some party, then part of that is gone. And they used for just a little while poor randomness, and because of another property of the elliptic curve cryptography, those private keys could be recovered, and coins of some hundreds users were stolen. Luckily, it was a good guy. People don't 100% agree, named BTC Robin Hood, and he tried to give back people their money. It didn't work all the time because often it's hard to find the owner of the address because of the anonymity thing, but at least a part of the money was returned. And some people said that's a new level of security as a service. If somebody, some Robin Hood makes tries to make you secure by getting at you and bringing your money to a safe place, and then informing you about the vulnerability. Maybe we can learn from that. So really, cloud vanity, that was our question. And there is services for that, like the Vanity pool. You see AppSpot, it's really cloud. And they have price lists and so on. You can order your Vanity address there. Here's the list of orders, and you can also help in, that's why it's called a pool, help in mining those or in calculating those, and you get rewards for that. This is examples of what people are looking for. Why can this be a good idea? We were talking so much about why you shouldn't do it, why it's insecure. It can be secure for one trick, and this was invented by Joel Katz, one of the big names in the Bitcoin ecosphere, in 2012 already. And this is maybe the most complicated slide for today. So what do? You generate a random private key A. So this is not the private key that you will later use to pay, to sign, but like you would create a private key, you create this random A. This should be good randomness. And then you compute the public key. Public key in elliptic curve, we already had it. It's just a multiplication with the generator. So this is easy to calculate. It's efficient. The other way around is not possible if the scheme isn't broken, but this we can do. And we publish our public key. So now anybody who likes to can try random Bs. People log into the pool and get the task, and then they start trying random Bs. And what they calculate is, now it's a little bit long because there are more steps to the address. We already said in the end you need the base 58. If we leave that away, there's some hashing in between. We can leave that away. So they basically calculate the public key that you gave them, A times G, plus the public key of the B that they just invented themselves. So they calculate their own public key. And then they give you back the result. The result means a B that leads to your Vanity address, something that starts with the right substring. And what you can do, and they cannot, and that's the most important part, you can compute A plus B, and this is the private key of the Vanity address, because in elliptic curve cryptography, it's the same calculating A plus B and the public key of that, or separately and adding them. That's one mathematical property of this scheme. So you can get to the A plus B, and they cannot because they never got the A from you. You just gave them the A times G, and there's no efficient way for them to get from the A times G, from the public key, to the A, to the private part of it. Because if the whole thing would be broken, this is not reversible. Okay. Okay, so if it's done right, and of course there's a lot of points where it can go wrong. For example, there could be a fake website pretending to be a pool using this mechanism, this trick, and they're not using it. Or there was even a pool that did it all the way, all secure, and then in the end they said, and now please enter your part of the private key, so we can conveniently give you the final thing. And boom, yeah, like it was okay until in the last step you gave him your secret and money was gone. So can we use it for other things? Secure cloud computation? Unfortunately, not so easily, because this is very special for certain crypto schemes that we have this kind of calculations. So it's kind of zero knowledge work. In this case, somebody works for you, but they don't get to know the secret part. This is basically a special case of homomorphic encryption. Special case because in homomorphic encryption you usually have a secret message. You don't really have a secret message here. But homomorphic encryption is calculations that can be done purely on ciphertext. And if you can do that, the holy grail of cloud privacy insurance, because you can securely have calculations done in the cloud with privacy kept assured. Unfortunately, there are no good homomorphic encryption schemes yet. There are a few partially homomorphic schemes where only a few very specialized computations are possible, like the example we saw, or in RSA without padding. And the fully homomorphic, where you can do all kinds of calculations like searching, filtering, sorting, adding, multiplication, and so on, are still being researched. They're either very, very, very slow or very inefficient for memory reasons, very complicated. But research is going on. I just Googled it today, so things are being are advancing here. Okay, malleability I will skip now because of the time, because you must be hungry. Yeah. Okay, in the end, coming back to the 7 virtues, our vanity that we want is part of the pride, so we're in the last line. And the good thing is, for every vice, for every sin, there's a virtue, something that you can practice, that you can use against it, that stands against it. And for pride, there's humility. So maybe that's, if you want a motto for this talk, humility. Be careful with what you outsource and to whom. It's possible, but with a lot of ifs. The thing I like most here, the greatest and the most important of all virtues, is said to be charity, generosity, and I think this is a nice motto for a whole profession. So give back to the community, do good stuff, don't be evil, and so on. And that's my talk. Thanks.
Thank you very much.